Have you ever wondered how a robot knows exactly how much pressure to apply when handling a delicate object, or how it feels its way through an intricate assembly task? It all comes down to its sense of touch, which is powered by specialized force sensors. Force sensor output signals are primarily classified into two fundamental categories: analog and digital. This classification describes the basic nature of how the measured physical force is converted into an electrical signal and transmitted for processing. The core reason behind these classifications lies in the way force data is represented and processed. Analog signals, for instance, are continuous electrical representations, typically voltage or current, that are directly proportional to the applied force. Imagine a dimmer switch. The light intensity changes smoothly with the turn of the knob. Similarly, an analog force sensor outputs a smoothly varying signal. On the other hand, digital signals representing force using discrete, binary values. These are like an on and off switch, but instead of just two states, there are many distinct levels that are represented by sequences of ones and zeros. This conversion from a continuous physical force to a discrete electrical value usually happens internally within the sensor itself, using an analog to digital converter. When selecting a force sensor for a robotic application, understanding these signal types is crucial. For applications requiring raw, high-resolution data and where custom signal conditioning is preferred, analog sensors might be a good fit. However, they are more susceptible to electrical noise and requiring careful shielding. Digital sensors, conversely, offer built-in noise immunity and often provide a more streamlined integration process as they can directly interface with microcontrollers and computers. This makes them particularly robust in noisy industrial environments. Beyond the primary analog or digital classification, force sensors also communicate via various signal types and protocols. You might encounter analog outputs as voltage signals or current loops, the latter being more resistant to signal degradation over long cables. Digital signals can be transmitted using serial communication protocols such as I2C, SPI, or UART, each offering different speeds and complexities for data transfer. Some sensors even provide pulse width modulation, where the force is encoded in the duration of a pulse. Additionally, some sensors are active, requiring external power, while passive sensors like some piezoelectric types generate their own signal when a force is applied. Ultimately, recognizing how force sensor output signals are classified and the various forms they take empowers roboticists and engineers to select the most suitable sensor for their specific needs. This informed decision-making leads to more reliable data acquisition, more precise force control, and ultimately, the development of highly responsive and robust robotic systems that can truly feel their environment with exceptional accuracy.
If you love robotics, like, subscribe, and keep building with us.